So C++ was originally standardized in 1998. For those of you who were using C++ in the 90s, you may not have realized it wasn't even standardized at the time. Pretty much after a little fix in 2003, the language kind of went stale for about 10 years. Not a lot changed. A lot of compilers were doing some cool stuff, but nothing really made it into the standard. And then in 2011, there was another new series of standards. We've had an 11, a 14, and now a 17 standard, and they're on to another one. So the pace of change can probably outstrip what most game developers have time to keep track of. So the first part of this talk, I'm going to cover a lot of where the standard is at, what's happening, how that relates to the Visual Studio tools for Microsoft platforms. In the second half, we'll talk a bit more about more practical stuff like build speed and iteration times. My name is Chuck Walburn. I'm in the Advanced Technology Group. In addition to spending a lot of time on my blog and on Stack Overflow telling people why they shouldn't use the DirectX SDK anymore, I also support about 6 different GitHub projects, DirectX Math, DirectX Toolkit, and the like. And as a result, I sit in a very interesting confluence of Win32 desktop, UWP, Xbox One development, even phone for a while. And I've kind of, through that history, ended up in sort of the C++ guru in our group. Although, to be honest, I've taken over from a long series of them. So the focus for my part of the talk is going to be around the Visual Studio product and how it relates to the conformance. I'll talk a little bit about a technology called C++ WinRT, which is related to the compiler. And then Andrew will take over and talk more about the optimizing build times on the 2012 product. So for those of you who are still on older versions of Visual Studio or haven't looked at 2017, I'm going to talk a bit about the high-level points here. These themselves I could do a whole talk on, but I just want to talk them briefly. So if you've fired up the 2017 installer, it's an entirely new experience. They've rewritten the whole experience to be much more lightweight. The install experience is now built around workloads instead of just sort of these random tasks that we used to have. The compiler is thought of as the 19.1 compiler. The 2015 product was the 19.0 compiler, so it's intended to be an incremental update. One of the big decisions in this particular update from 2015 to 2017 is the goal to maintain binary compatibility. So historically, if you built with, say, 2012, a static library from 2012 won't link with 2013. And this time they made a concerted effort to keep the memory layouts the same, the library compatible. Mostly this has the impact of making it much easier to adopt 2017 if you have 2015 versions of middleware and other third-party packages. It supports on the same basic development OS as the 2015 product, Windows 7 SP1 and up. And it still targets the same desktop apps environments we've supported for quite a while. Vista, Service Pack 2, Windows 7 SP1, Windows 8, Windows 10. And it will even support Windows XP Service Pack 3. I don't want to go heavily into that. There are some caveats that are linked to in the talk when it goes public here in a little while. You can also find that information on my blog. A lot of the focus in the 2012, I'm going to keep saying 2012 this whole time. The 2017 key improvements around the IDE, there's a lot of focus on startup time, just getting the solutions to load faster, use less memory overall. And as with most of these environments that have rich extension systems, often the slowdowns you don't realize are due to third-party extensions or something you've installed. So there was some effort in the 2017 IDE to make it clearer to find out who's taking your time to load up. And in general, there's been a lot of focus on how to make the IDE work well with large monolithic projects, which is almost universally games. Historically, Visual Studio has had trouble with solutions with 100 projects in it that end up generating 150 meg executable, and a lot of that work has been focus of this release. There's also been some specific feature work around link times. A lot of the analysis of build times in games, most of it is around the link step is what's taking a lot of time. So when you're trying to make one tweak and you try something, it's actually the linker that's slowing you down. And we'll talk a bit about that a little later. And in addition to all the stuff I'm going to talk about around native code development, there's been a big focus in the Visual Studio team around just enabling open source generally and being more friendly to open source. I've gotten some of the weirdest email I've ever gotten at Microsoft in the last few years about open source. But it's been a good pattern to see the company more open to it. So there's direct support for CMake projects. You can open up a raw folder even without an SLN or a VC proj and do some IntelliSense and some building. So it's pretty cool for just working with small libraries. And there is support for non-Microsoft platforms within the IDE. as Visual Studio is really trying to be a one-stop development shop for a lot of different platforms. Won't talk a lot about the specifics of those, but there are blog links in the talk you can go to. Okay, so the first thing to keep in mind when you load up Visual Studio is you're going to be presented with this long list of workloads, and it can be a little confusing as to where to start with. There is a workload labeled game development with C++, kind of gives you an initial starting point. This is more focused on some of the middleware engines that are integrated into the product, but it's a good place to start. If you're looking to do desktop development, there's a separate workload for that adds mostly the libraries around Windows desktop development. And then for UWP development, there's another one that adds UWP packaging. The main thing to keep in mind when you select the UWP workload is that is basically JavaScript plus HTML and C# plus some basic packaging. If you actually want C++ development for UWP, you've got to look through and find this optional feature to turn it on. If you're an Xbox One developer, you already had to have the UWP package on just to get the packaging tools, for example. So there's been a lot of updates to Visual Studio 2017 since it came out. If you were using 2015, you probably saw 3 updates over about, a 6-month period between each. With 2017, they're more like 6-week cycles, so there's been a lot of updates, and it can be a little hard to keep track of. So I started to summarize the history of the release since RTM, and a lot of the initial 15.1, for example, was just to add the new Windows SDK. There wasn't a compiler change. 15.2, there wasn't a compiler change there. They just added some CMake stuff. But then in 15.3, we got a big update to the compiler. 15.5 was another update. 15.6 is a minor one. 15.7 is already in preview. So if you're on one of these older ones, you definitely want to be aware of what the differences are and help keep track of that. And I'll go through some of the practical implications here in a minute. So when you get when a new update comes out, the first time you usually notice is there's a notification, a little yellow flag that appears up in the top of the IDE. And if you do that, typically that will only flag a couple weeks after the release because there's a staged release for it. If you read about a blog post about a new release and you want to try it out right away, sometimes you have to go to the download site, download the latest installer, and that'll force the update right then. Sometimes it'll take a day or two. It just depends on how long the cloud data takes to propagate. So I'm going to change gears a little bit and talk more about the language conformance for a little bit. So the product supports all the C++ 11 features. These were mostly in place for Visual Studio 2015 Update 3. I'm not going to go through all of them, but these are most of the ones you've talked about or probably already familiar with. A lot of useful stuff in here, move operators, null pointer, magic statics for threading, that kind of stuff's all standardized. To keep in mind, C++ 11 was the first time the C++ standard recognized that multi-threading was part of the standard. That was always been extensions before then. A lot of work around Unicodes and interesting concepts. And then the stuff I'll talk about all builds on this platform. So the Visual C++, Clang, and GCC compiler do not implement the C++ 11 extended integer types. If you look at those are considered optional. There's a feature called expression esfine, which means substitution failure is not an error. It's a specific meta template feature. The compiler team considers it pretty useful the way it's implemented, and it was added in update 1 initially, and then it's been changed since then. You can use it for STL, you can use it for Boost, there's some other libraries, but they don't quite have 100% of the scenarios nailed down for that just yet. Another notable conformance difference is that the preprocessor is not truly a C99 compliant processor. There's some notable bugs in the variadic macro implementation, so it can be a little fragile. And then there's a feature called two-phase name lookup, which I'll talk about here in a minute, that's still in development. So the Visual Studio 2015 Update 3 added some of these. 2017 has more of these C++ 14 features. A lot of this focus for C++ 14 as a standard was to fix up bugs and other issues they found in C++ 11, so you can think of it as a servicing version. Some things are just useful little syntax candy, like some binary literals or things like that were existed in C11 that they wanted to move over. There's always been a sized new, but there wasn't a size delete to go along with it in case you had some specialized size-based allocator. They defined a bunch of attributes in C++ 11, or the mechanism for attributes, but they didn't actually provide useful attributes in the standard. So they've started adding one. The first one here is deprecated. So you actually have a canonically standard importable way to indicate something needs to be deprecated. And then a lot of the focus around C++ 14 was just generalizing some of the functionality in 11, make it more useful in more cases. I'm not going to go into all the details there. So the other half of the standard, in addition to the language, is, of course, the standard library. The C++ 14 standard library had a bunch of stuff that was added to the language for C++ 11, but the standard library itself didn't leverage it. For example, const expression and no except. There were little oversights, like there was a make shared, but there wasn't a make unique. They added the concept of user-defined literals to the language, but they didn't use them in the standard library, so they added those. By reference, the C++ 11 standard and the C++ 14 standard also require that the conforming compilers support C99 standard library. This was kind of a last-minute add to the spec. So that's stuff like roundf and floorf and things like that. And if you looked at Visual Studio, historically, it's not had these C99 functions. So those started showing up in 2013. So there's been a lot of work to get the language up to the whole compiler and Visual Studio product up to conforming. And then the question was, well, how do we handle moving forward? Because there's already a C17 standard in the process at the time. And GCC and these other libraries have very fine-grained ways to control which version. So Visual Studio compromised to basically have only 2 modes, maybe 3 if you look at it, depending on how. So in 2015 Update 3 and 2017, there's a switch called STD. And you can set it, by default, it's set the same thing as C++ 14, so that means the compiler is C++ 14 conforming. And then if you want to opt into C17, with 2015, you had to say stood latest, because there wasn't a C++ 17 at the time. And with 2017, there's now C++ 17, and then stood latest will eventually mean C20 or something else. Prior to 2017, the 15.3 update, which was the third update I mentioned earlier, you had to set this through additional options, but they finally added it to the IDE. And you can actually see it called out here. If you're doing portable open source libraries, one of the things you might run into is the definition of C++. Everyone's used to doing an if-def on this for around C++ versus C code, but it turns out that macro actually has a defined value in the standard. C++ has reported 1997-11 for pretty much its entire life. There's been a lot of question of when to change that. And certainly some of the Visual Studio team is, I believe the quote from one of them is, we might break the internet if we change that too soon. So as a compromise, they added a new macro, this MSVC lang, that actually reports the value you would expect. In this case, in C++ 14 mode, it would report 2014-02, and in C++ 17, it reports 2017-03, which are defined in the standard. And this actually ties into something I'll talk about here in a minute. It's really not so much about the language as much about the two-phase lookup and the preprocessor. Another new feature that was added in 2017 is the permissive minus switch. There's been a switch in the language for some time, in the Visual Studio product called /ZA that was supposed to be the sort of ANSI conformant portability switch. That thing has not really been changed since 1998, so it's not very useful. For example, anonymous unions aren't technically ANSI compliant, but those are part of standard C++ 11 to these days. So permissive minus is intended to sort of take over that role of if you throw this switch, you'll be a little more conforming. We'll shut off some pretty subtle Microsoft extensions that you may not realize you'll be using, and you can make your code much more portable and clean. There's a couple of specific subsets this relates to that I call out here. You can control them individually. The big thing with permissive minus is that you need to have a Windows SDK that's been cleaned up for all these new switches, because a lot of the older SDKs aren't permissive minus compliant. Most of this stuff was fixed in the Windows 10 Creators Update, and then more of it was fixed in the Fall Update. And much like the /std switch, the permissive switch wasn't part of the IDE until very recently. The main thing to note about permissive minus is if you can build with it, it actually will improve throughput. The whole parser is a little less complicated in the permissive minus code paths because it doesn't have to look for some of these extensions, so you can actually get some throughput improvements. Okay, so two-phase name lookup is a very fancy way to describe this feature, and I'll try to summarize it. For the history of Visual Studio, there's basically two ways to think of templates. Templates can either be thought of as macros, which means that you just kind of gather up what the developer provides, and then when it gets instantiated, you actually try to compile it. Or they can be thought of as actual code that you evaluate when you see it, and then you go and evaluate it some more when you embed it where it belongs. Visual Studio chose sort of the original macro definition. The standard finalized in 1998 actually chose the other definition, and this has been a subtle area of conformance for some time. Now in Visual Studio 2017, when you turn on permissive minus, it actually will use two-phase name lookup. There are some cases where it's not fully implemented, so if you're using the C++ CX extensions or OpenMP, you're going to get a warning saying this doesn't quite work. You can actually get the subset of that by using permissive minus without two-phase using that ZC switch. And I'll show you an example exactly what this looks like in code. So we had a header combase.h where there was a template up here. This IID PPV args was defined. And you'll note that it's doing a static cast to IUnknown star. But in order for that to do that, the compiler actually needs to know what is IUnknown besides a class. Now this is always compiled in Visual Studio because we don't evaluate the template until you instantiate it later. But with two-phase name lookup, this actually fails to compile. And the reason is that IUnknown isn't actually defined until later in the file. So there's two ways to fix that. You can just add a forward, or in the case of this one where they were a little concerned about moving things around too much, they just put a declaration up above so that it's clearly defined, but the actual body of the template doesn't appear until after the IUnknown is defined. You probably have a number of cases like this in your code, and you won't see it until the first time you try it. But technically speaking, this code was not conformant to C++ 98, much less C++ 11. This code actually is conformant. Okay, so C17 was approved back in March 2017. The final version of the standard was published in December 2017. Just as a note, they've already started working on C++ 20, which has a lot of crazy stuff in it. My favorite is what they call the spaceship operator, which is this idea of doing string comparisons in a single overload minus greater than or equal. We'll see whether that survives the ratification process or not. I'll talk about it in some future talk. So the next couple slides, I'm just trying to categorize where all these different C++ 17 features come in. I certainly don't expect you to memorize these charts by any means. Mostly what I'm trying to communicate is there's been this phased work where ever since RTM, they've started to add a few C17 features over time. These are all tied to the new STUD C++ 17 flag. Some stuff like try-gaps were actually removed a long time ago. They were removed in, I think, 2012 or 2013. If you go read some of the standards links, which I provide in the talk, you'll see that pretty much only one vendor in the world cared about this feature, so it was not a big deal. There are some things like nested namespace definitions, where instead of having to have name A bracket, namespace B bracket, namespace C bracket, you can just kind of define them all at once. We actually leverage those in the C++ 1RT standard. Some of these are just convenience, static assert where you don't have to provide the message. Mostly I think that was to help localization. There's more work in C17 to make const expressions more generally useful. There's a cool thing called if const expression where you can in a template evaluate whether something actually is a constant expression and use a different code path at build time. We finally have a macro has include, which will let you determine if a standard header is present. Unfortunately, that's not present when we needed it in the old ones. A couple new attributes, some new construction rules. A lot of this stuff just cleans up things. One of the things to note about C++ 17, though, is the things that were declared deprecated in C++ 14 are actually supposed to be removed by C++ 17, so you can potentially end up with some code breaks that I'll talk about. For example, who knew there was a ++ operator for bool? It's gone now. Probably another big change to note is that the concept of no except in C17 was actually introduced in C++11. In C17, it's a little more strongly defined, and I think I talk about it more in a moment, where no except is actually part of the type system, so you actually can get two overloads will disagree if they're not the same exceptions. Some concepts of over-aligned dynamic memory, which means that you actually have a concept of aligning in the standard, which is great. It's always been platform specific at the time. Some of the weirder things like inline variables, this takes a little bit of time to understand what that means. Basically, that means that you can declare a variable, mark it inline in a header, and then you don't have to go figure out where one of them canonically is extern and one of them isn't. Mostly it helps if you're doing all header implementations. Some things, the dynamic exception specifiers, I think I'll talk about that in just a moment. Those are actually removed from the standard. And then most recently in 15.6, they added another optimization. Originally, the 15.6 list was supposed to be quite long, and then someone realized it was happening over Christmas, so it got shortened to one feature. And everything else got pushed to 15.7. So the plan is by the end of 15.7 here in the next few months, we'll have a first pass of all the C++17 features implemented, with two notable exceptions, which I think I'll get to in a moment. So the C++ standard for 17 also has a standard library, and there's some new headers in it. I'm not going to get into all the details. You can look up this on a CPP reference or something like that. The main ones to note is that the 15.7 update file system's been there for a while, but it's not been standardized. There's a V3 version that's part of the final standard that we should have in 15.7. And then there's a few of these scientific specific functions, some like hypotenuse functions and things that are supposed to show up in 15.7 as well, but most everything else is already there as of 15.6. As I mentioned, in C17, things that were supposed to be deprecated in C+14 are actually gone. So if you build in C17 mode, some code that uses these old functions will actually fail. Ideally, you clean all that up. There is a macro you can define to put them back temporarily if you want to just unblock your build and move forward. There is a reference in C17 that the C17 standard library needs to be conformant to the C11 standard library. As it turns out, though, there really isn't much work involved because a lot of it is considered optional if it's already covered by C++ features. Really, the only thing that's new, for example, is align DALEC, which is an official portable way to align memory. We've had an underscore aligned malloc for a long time, but it's a more portable version. Here we go. So C++, WinRT, and the C++ language extensions make use of C++ exceptions, so it's important to call this out. In the C++17 language, no except is now part of the type system, so you'll actually get some warnings if you have things decorated differently. Traditionally, there was a concept added, I believe, in C++ 2003. It was well-intentioned. The idea was, in a function, you should be able to declare that this function never throws any exception, this function throws these specific exceptions, or this function can throw pretty much any exception. And the hope was that optimizers could make use of that information. And I think it's largely be considered not useful to most optimizers to have that information because you almost always end up being conservative about it. So the new standard that was introduced with C++11 and sort of finalized in C++17 is a function either throws or it throws nothing. There's no really in between. So if you use these throw ... which meant I can throw anything, or throw this list of exceptions, those are considered deprecated, and you'll now get warnings saying, hey, you probably shouldn't use these. And just for simplicity, if you do throw blank, which was the old way of saying I don't throw exceptions, that gets accepted as an alias for no exception. You'll see this if you have some of this kind of code. You'll get some warnings you might not see before, and it's usually related to this. If for whatever reason you're dealing with middleware or something else and this just gets to be too painful for you to deal with right now, you can turn it off in the short run with the ZC switch. Keeping in mind that your code won't be C++17 conformant until you fix that. There are a few other conformant switches to be aware of in the Visual Studio 2017 product. When const expression was originally added to 2015, there was some debate about what exactly an extern const expression meant, and then the standard clarified what it meant. So you actually have two different behaviors So in the old compiler, if you had an extern const expression, it ignored the extern part. So you can still get back to that behavior if for some reason you depend on it. A long time ago in the C++ 11 standard, and I think even before, new was defined as always throwing. So if new runs out of memory, it's supposed to throw an exception. The only time you ever use new and don't get an exception, where you actually test for null, is specifically when you provide stood no throw as an optional parameter. Interestingly enough, the compiler has still generated code as if it could return null for a very long time. So if you look at the code gen, it calls new, checks for null, then calls the constructor, even though we just said that it's never a case that's going to happen. So there's actually a switch that they're going to eventually turn on by default, where you can tell the compiler, hey, just stop doing that extra test for null. It's completely pointless. And that's the ZC throwing new one. That's actually been around since 2015 update 3, but it's still off by default, although they expect to flip that at some point. Okay, so I'm going to blast through this last little section before handing it off to Andrew. So we have, for those of you who've done UWPE or even Xbox One development, the initial thrust of that is through something called C++ CX, which are the hats. As an alternative to that, there's been a project going on called Modern C++ or Modern Windows Runtime. The projections are called C++ WinRT. And the idea is that instead of using language extensions, we can actually embed the whole thing in C++ 17 standard language features. So you don't need the ZW switch to use these. They make use of the C++ 17 nested namespace features. They work well with STL containers. It's all pretty well integrated. I can't go into all the details here, so I suggest you follow up. There's a couple blog posts you can find on the internet. The main thing to remember is that GitHub, the CPP WinRT. I have some templates that you can try out as well if you're interested in looking at this. Just to give you a quick idea, this is what classic C++ CX code looks like. You have that ref class type. Part of the confusion with C++ CX is they reuse the reserve words from managed C++, so that's even more confusing to people. There's no C++.NET runtime stuff happening here at all, but we use the same keywords. So a ref class is one of these C++ CX extensions. And then to add an event handler, you hand one of these ref new things and use pluses. This code's kind of all over MSDN right now. That same code as a C++ WinRT projection. This is all done with headers. There's no magic at all. There's no compiler magic. And it's just done through a slightly different method through templates. And the net result of the code gen actually is quite a bit better. And I'll talk about that in a minute. So we introduced C++ WinRT using Visual Studio 2015 Update 3 initially. And with 2017, there's some new features they're able to take advantage of. So there's been a lot of work optimizing it. One of the things that was a little niggly was in 2015 Update 3, it was pretty easy to consume Windows Runtime APIs, but it was not so easy to author Windows Runtime APIs. And for the most part in games, that didn't matter, but if you were doing XAML UIs or something, it was really painful. But there are a few cases, particularly around vector view and a few others, where you're actually technically producing a type, and that was really hard to do with C++ WinRT. And then with the latest version, the compiler is actually able to take advantage of C++ 14 const expression and have it evaluated all at runtime. So it sort of emulates the old compiler magic. There's also been some work to improve debugging. In 2015, it was hard to see properties, whereas with C++ CX, it was easy to see them. The other thing is, up to now, C++ WinRT projections have been something you download off the internet. You can either use NuGet or get it off the project. Though they're actually being integrated into the next Windows 10 SDK. I actually don't know what the official name's going to be. The rumor is the Spring Creators SDK, so I've just put that there for now. But there is a specific blog post that talks about this. And the more interesting thing is not merely that the projections are there, but the compiler that generates those headers is there. So if you have anything with a WinMD, a middleware, or anything else, you can run the compiler on it and generate the projections yourself and not have to use C++ CX to consume them. Okay, with that, I'm going to yield my time to Andrew, and then we'll come back at the end for questions.
Hey, my name's Andrew Ferrier, also a software engineer like Chuck in the Xbox Advanced Technology group. I tend to focus on basically CPU systems, multi-threading, that kind of stuff. And today, I want to talk about basically how to optimize your builds, mostly around optimizing your iteration times or that F7 time after you change like one line of source code. Because that's usually what you're doing on most of your day-to-day development. If you can save a couple minutes off that for each one of your builds, that easily adds up to over an hour a day that you're just not sitting around. As Chuck mentioned previously, the Visual Studio team hasn't really focused that much on games. It's more they haven't focused on these large monolithic projects because traditionally Office, Windows, all those kind of things are just made up of a lot of DLLs. So they all tend to be pretty small little things. So this is one of the focuses for 2017 is to handle those larger projects. So there are 3 key settings that can drastically impact your build times. And along with these settings, there's also some coding patterns we're going to cover that can seriously impact your build times. And lastly, I'm going to show you some of the tools that actually are available to find out where the hotspots are within your build. So first recommendation for our bare minimum set is use precompiled header files. This sounds like pretty much almost like a no-brainer. They speed up your builds. However, we did a full developer survey of a lot of AAA games out there last year, and we found about 50% of the studios don't use them at all. A lot of studios like to use map files for symbol lookup at runtime as opposed to doing lookups in the PDBs. This is usually on more console development because it's just because of memory constraints, it's just not feasible to look up, to put the PDBs over there and process them. And so that's why they use the map files. However, for your day-to-day iteration development, the developer is there with the debugger, which has the PDB files, so you don't want to generate those maps. The time at the end of the link step, it's got to merge all the individual PDBs from your libraries into one final massive PDB. There's an option in there called debug fast link, and it skips that step. And this can actually save you a lot of time. It's also, again, not needed for your day-to-day development because all the supplied tools fully support the fast link PDBs. So let's start with PCH files. For those that don't know what these are, effectively, the compiler is going to process all the headers once, precompile them, save that out as a binary blob. Then each of your later source files that use that PCH file, it just does a block load into memory and is done. It doesn't have to process the source files at all. It doesn't have to parse any of the headers. It's usually pretty common to have one PCH file per library. So when used effectively, they can create a pretty drastic reduction in your build time. A game I was working on a couple years back, I was kind of upset because our full build times were pretty expensive. So I decided to go through and figure out why that problem was. And I found out it was because of the way they're generating their PCH files. So I went through and effectively changed the formula for creation of the PCH files. Their formula was only headers that were stable for about 6 months or system headers, the only things to put in the PCH. And so I changed that rule to be stable for about a week or used more than 75% of the source files within the library. And that one change dropped full build times down to half. And for the day-to-day work, a developer is usually not changing any of these core header files that much. If they really are one specific header file used only in one place, they can always pull it out. But because of this rule of a header file that's used in at least, say, 75% of the files in the library, it still is cheaper to leave it in the PCH file because you're going to have to rebuild all those source files anyway if you change that header. So the general rule is be aggressive on what you're putting in your PCH files as opposed to being totally conservative. So basically more than just those basic system headers. It's actually possible, if you're not using PCH files right now, it's possible to test their usage without changing any source at all with these 2 compiler options. /yu will actually let you create a PCH file. Then /fi basically is a force include. It's basically the same as putting #include at the top of any of your source files. So I want to show you the math. Here's some of why they're always helpful. So here's a sample that I built for one of my libraries. You can see at the bottom, it takes about 5.82 seconds to build this particular library. Each file took between half a second to a second to build. Here I have the PCH file, and it's dropped it down to 2.37 seconds for that one change. However, this is the part that's important to look at. And what that delta is, you'll see the PCH took about half a second to build, but that time is almost exactly subtracted from every single source file. And that's where all that time savings come from, is that block load that's coming in. I know a lot of titles like to use what we call single compilation builds, blob builds, lump builds. They have a lot of different names. One of the reasons is because you're reducing the number of header files you're processing. However, even with those, you're still getting better performance if you add the PCH file. This is the math that backs everything up. So what basically happens is here, these are the only numbers that are important. It's the number of source files you have that are in your library that are using it, the number of source files that you depend on a header. On average, N1 and N2 are about the same. And there you can see at the bottom, basically the number of source files is your multiplier. And so the more source files that are using the PCH, everything is just exactly subtracted. So even if you're using blob builds, the only thing you've really changed is that N1. But the first part is still there, basically dominating your time. So we tell people not to generate map files. The reason why is they're incredibly expensive to generate. Usually your link time is usually 20 to 30 minutes, or 20 to 30% of that link time. I guess one thing I want to call out that I actually forgot to mention at the beginning, so all these times that you're seeing up here, this is actually, it's a single line change to an actual real world title. So it's actually from a real game, it's not a made up metric just to show off things. So basically if you have /map on your link step, remove it. You'll save yourself a lot of time. Again, for your day-to-day iteration work, you've already got the debugger. It's got the symbols for the PDB. Even if you're working on a console, again, the debugger has the PDB. There's no reason to process that map file on the code itself. The blog post there is from the Visual Studio team, and it pretty much says the exact same thing, but also gives you some more tools to help you figure out how to use what we call the debug interface access SDK or DIA to process the PDBs yourself. But as you say, they're in 15.6. All of a sudden, map files are free to generate. Well, it's not quite true. There was a change made in 15.6 to map file creation, so they're built in parallel now with Link. Previously, they were sequential. However, if with some of the other steps that you do here, it can still end up as the dominating time, even though it's being built in parallel. For this particular set of options here, it was not the dominating time, so it ends up down at 0. So at the very end of the link step, it merges all the individual PDBs from your libraries into one massive mega PDB. This actually gets pretty expensive. It's also not an incremental step, so even if you make one change, it still has to merge all the PDBs back into that one big PDB. And that right there is about half your link time from just changing one line of code. There is an option to turn this off. This is called Debug Fast Link. It skips that final generated PDB, and what it actually includes, the PDBs reference data back in the individual OBJs, all of them that were used to build your title. And again, for the local iteration builds, the developer already has the debugger there. It fully understands PDBs, the FastLink PDBs, all the Microsoft tools, fully understand them. Previous versions of, especially in 2015 and earlier versions of 2017, did have some issues with the FastLink PDBs. They came around memory usage. It would effectively, memory would start to bloat, and this actually would start causing some correctness issues and stability issues. These, as of 15.3, have been resolved. Memory usage is the same for the debugger between the two. And more importantly, they've fixed a lot of the correctness issues that can show up. There have been issues with certain network distributed build systems not supporting or not working well with FastLink. And this is entirely around those OBJ files. They need to be back on the developer's machine so the debugger can find them. If there's some network distributed build systems, just leave those off on whatever that network share is. So whatever system you're using, make sure to pull those back to your original machine. Also should be noted if you're using link time code generation, debug fastlink doesn't work, but also for your day-to-day iteration builds, you probably shouldn't be using link time code generation. As we all know, that takes a little bit of time during your link step. Sometimes though, your developer has a build, you want to give it off to test, so you do want that final monolith PDB. It's pretty straightforward to generate one from your build. There's just this option right there, which is build full program database. It's the exact same step that happens at the link. I want to call out this unreferenced symbol removal. Basically, just removing all your data and your functions that aren't being called. It can actually both increase and decrease your build times. If you actually turn this off, so you leave all the unreferenced symbols in, that's a lot more data to process for your PDBs and your maps and such. And so they can actually increase your link time. The reason I really want to call this out is because there's an interesting side effect. It shows you how much cruft you have sitting around in your code base. That's just taking time to build. I've seen this in a lot of game engines that have grown organically over the years. As new features get added, old code is deprecated, but still sitting around the code base. Also in engines that are designed to support all sorts of different types of titles. And the idea, all this code, even though it's never being used, is still counting against you for your build times because it's being compiled, it's just being thrown away at the very end. There, you can get a feel for how much cruft is in your code base by using this option. Just look at the final executable size. For most of the titles I looked at, it's usually between a 5 and 15% difference in executable size. That's kind of an idea of how much extra stuff is sitting around. This is the output from the linker. It'll tell you what it's been removing. This is just from one of our random ATG samples. You can see I've just removed some pieces of data that I never used for these colors, this resource barrier function. So now I know I can just go delete that code and I'll never spend any time compiling it. So I can just remove it as old dead code. So it's well known during what we call the front end and the back end, C1, xx.dll, and C2.dll. Basically, it's the parsing and then the code generation. That this MS-PDB service is basically a bottleneck in those build times. The main issue is it's all this traffic between the compiler and it. It basically sends type information over to the service, which sends back IDs to keep a unified set of IDs across all your source files. However, there's been a hidden flag within Visual Studio that actually optimizes this step. Basically, we're going to tell you about it here today. It's been around probably since 15.3. And so it's this /ZF option. All you have to do is just add it to your compiler, basically as a compiler flag. However, if you're not using PDBs, if you're using /Z7, where it stores the debug information directly within the OBJ files, this option doesn't work because obviously you're not using the PDB service. So I know some network distributed build systems require Z7, so it's not going to help you. So the question is, why would you want to use this flag? Within our full real title here, just turning that flag on reduced our full build time from 28 minutes down to 23 seconds. Or 23 minutes. And that's, yeah, 23 seconds would be nice. This 25% reduction, we've actually seen pretty much at least across the board for all the titles we've looked at and other pieces like, building Chromium or whatever. So give it a shot, try it out on yours. But again, if you're using Z7, it's not going to work for you. Basically, all the other variants, such as ZI and such that use PDBs, it will work for you. So what gotchas exist directly in your code that are hurting your build performance? Force inline, or how to basically shoot yourself in the foot really easily. So if you add force inline to a function, it disables all heuristics that the compiler decides to use, whether to inline a function or not. Because it's always honored if it's possible. Obviously, you can't inline, force inline a recursive function, for instance, so that'll actually not do it. So the compiler's taking it very seriously. It's immune from all budget checks or heuristics for whether it should inline that function. More importantly, it does not affect any of the heuristics for any other functions, whether it should be inlined or not. It's totally ignored for any of that math. It's always honored. So the bottleneck comes in how Visual Studio handles force inline. And It's because what it does is it inlines the pre-optimized version of the function directly within every place it's being inlined. It does this because it gives more optimization choices later within the code generation step. However, this means it has to redo a lot of work because everywhere that function's been inlined, it now is compiling that function every single time. So if you inline it in 100,000 places, you're now compiling that function 100,000 times. And this can actually easily lead to a couple pathological cases. The first one is, as your outer function starts getting larger, Visual Studio has these thresholds where it'll start backing off on optimization choices. There's two thresholds. The first threshold, the basic one is it turns on, leaves all your optimization choices on. Once you go past the next threshold, it turns off what's called the points to optimization. This is where it tries to figure out if two variables are really the same variable or not. This happens a lot with parameters that are going into these inline functions. And the last case, if the function gets too big, it actually disables the optimizer totally on that function. That last threshold, though, is incredibly large. We see it very rarely across the entire Microsoft code base, but it is there. I'm actually haven't seen it from any game code at all yet, because it's pretty obvious when you see it because the optimizer is disabled. And you actually can get a lot of code bloat as well from this force inline, which causes more weight on, or more contention on your instruction cache, obviously. So there's a good chance this indiscriminate usage is actually hurting your title. So last fall, this website was going around, basically showing, look, this is how bad Visual Studio is and how much time it takes when I'm force inlining all this code. So I actually want to show it to you. Here's this is the type of code they're doing. It's pretty standard game math. You've got your add, subtracts, dot products, square roots, and such. The difference between these two runs is there's this top level function that's force inline or not that's just calling a lot of these math functions. And of course, they're all innocuous math functions that a lot of titles tend to force inline. This is a pathological case, but it's going to show you clearly what issues end up resulting. So 2015 was hit pretty hard by this egregious case. Here our build time for this one single file console app was 8 minutes. The execution time was 6 seconds. If you look at the code generation time here at the end, you can see all that time was taken in main, which was calling this one function that was force inline that then called all these math functions several times. Making one change, just changing this one top level function to not be force inlined, dropped our build time down from 8 minutes to 8 seconds. More importantly, it dropped the execution time down from 6.5 seconds to 1.5 seconds. Sure, this function is a special case, a pathological case to kind of show you what can happen, but imagine little things like this scattered throughout your code, which is easily a death by 1,000 cuts that's almost impossible to find. We've seen similar issues in the DirectX math code. Basically, you increase of execution size. Within the actual test code, though, the functions don't get large enough for the optimizer to back off, so the execution time stays the same, but executable is larger. And it's actually one of the reasons none of the DirectX math code is actually force inline. The compiler does a much better job on its own. For this particular example, the number of inline functions was 200 in the good case. The bad case, it was over 10,000. I did want to call out, I got an interesting code generation bug that was sent to me from a real title in one of their animation functions. They were like, you're generating some really bad code. Why are you doing these back-to-back stores onto the stack of the exact same data? Basically back-to-back move instructions. And what it came down to was, it was a simple animation function. It's about 430 lines of code. Not that bad. But because they had all these little innocuous force inlines all throughout their math library, that function ended up at 16,000 lines of code. And so they hit that disabling of the points to check. So basically all they had to do was all they did was get rid of all their force inlines. All of a sudden their builds got faster, their code ran faster, everything. So usually it's one recommendation I give people, just do a search replace and delete force inline and see what happens. So for the compile times, the actual 15.5 update fixed a lot of this. Basically what they added was an inline cache. And it's a cache of the compiled inline function. So it doesn't have to redo as much work. And basically a function's added to the cache based on how many times it's been seen. The default is if the function's been seen at least 100 times, it's then added to the cache. There are pros and cons to the cache. Obviously, it's going to take more memory for your build, but your build times improve. If you want to, you can control the size of the cache with the /d2 func cache. There's a typo there. There should not be a space between the E and the number. Default's 100. You can set it up pretty much as high as you want. If you set it to 0, we'll turn off the cache. Here you can see the default cache size for that egregious case. We went from 8 minutes down to 23 seconds. More importantly, though, the actual execution time dropped as well because it's caching, basically, it's not the pre-optimized code anymore. It's caching code that's already been compiled. And so you're not hitting these really large functions that are causing the optimizer to back off. So it's common knowledge that the compiler can do more than one source file at a time. Obviously, we also have distributed build systems, so we should all be using multiple processor builds. However, there is a gotcha to watch out for, and that's resource contention. So how many people here know that virtual alloc can actually time out? So if you set Windows to manage your page file size, what happens is, so virtual alloc, whenever you request a block of memory, a backing area in the page file has to be allocated at the same time. So when you start doing these large builds where you start requesting 30 to 50 gigs of memory, it has to go ask Windows to increase the size of that backing page file if it's the one managing it, because it's not going to do a full size. Now the compiler is doing so many requests to virtual alloc, it backs up on the file system. Virtual alloc for later requests eventually time out and just return null. So what happens is that's when you get these out of memory errors coming back from the compiler, and you're like, I'm only using 30 gigs on my 64 gig machine, what the heck? And it gives you these weird errors about increasing the heap size. That message is actually wrong. This is actually what's happening. The recent changes of recent updates to 2017, they actually fixed the error message so it's correct and gives you pointers to how to change it. Basically, the easiest way to fix it is pre-allocate your page file within the system settings, just to be as large as you need it to be. There can also be a sweet spot based on number of cores being used for this title's limit of parallel tasks that can be performed based on dependencies. These are my build numbers across multiple cores. I had plenty of memory in this machine, even though it took about 50 gigs to do this for a full build here. And also, all the code was coming off an NVMe, very fast one, and my page file was still on NVMe. But I still ended up, there's this sweet spot. Using more than 6 cores didn't actually help the build. Usually, like faster hard drives can get a bit better, more cores. But we usually recommend, instead of adding more cores to your build machines, get faster cores, and you'll probably increase your build performance. Visual Studio is seeing a lot of internal changes. Chuck's already covered a lot of them for the C++ side. Some of these internal ones tend to be hidden inside the blogs. The biggest one, the linkers received the most improvements, and it all really comes down to being a lot more multi-threaded. Previously, it technically was multi-threaded, but it held locks for a really long time, which tended to serialize a lot of stuff. They've dropped the amount of times locks are being held to parallelize a lot better. We've seen on average about a 10% speed up in link time code generation. We have actually seen some titles get a 50% speed up in link time code generation. It all depends on what you're using. You can control the number of threads it's using with the /cg threads option. The default is 4. Previously in 2015, it was the max you could set was 8. Now you can set it up to 32 or higher. Try a higher number, see if it helps you. There are restrictions to scaling, though. The compiler will not compile a function until it's compiled all of its callees. Did I get that in the right order? Yes, all the callees, because it helps improve the optimizer. However, functions above a certain size threshold are exempt from this. They can just be built. The idea is to keep these really large functions all of a sudden at the very end are becoming a long pole, and you end up going single-threaded at the end. So what they did was they dropped the size of this threshold so more of them can be built in parallel. We haven't seen any decrements in code generation quality. And the interesting thing was at the higher threshold, I think within the Windows build itself, they probably saw it maybe at most for a dozen times for a dozen functions and dropping it. So they dropped it down. So they get, basically it's better performance because more can be built in parallel. Again, we talked about it before. Debug FastLink. We've actually fixed a lot of the bugs it had. So please try it again. Yes, the entire Windows and Office build system always use the latest version of 2017 for its builds. Hopefully we find all the bugs before it goes out. Yes, we do admit some get out there, as you've seen on many blog posts. But Microsoft is very much into, as we say, eating our own dog food, which is we always use everything internally, the latest versions, including pre-release versions. So next question, how do you find these hotspots in your code? Like you may have a function that takes 10 seconds. Yes, we have a timer, Clint. The performance summary, this is /CG summary option, gives you this nice little thing at the end for your build timings. This highlighted case, custom build, you can see, I'm calling it 4 times, taking 8 seconds. Is that expected for my custom stuff? /BT plus on the compiler gives you the amount of time for every source file in each step. This is the front end, C1XX. You can see how much time I've spent for each source file. C2 or the back end, this is the code generation, how much time is being spent on each file. If you're doing link time code generation, this is pushed all the way to the end. The linker itself is calling C2 as opposed to the compiler. Again, here's this CG summary /D2. These are technically undocumented flags, but they've been around forever. If you're using link time code generation, use the version on the right for the linker. It's because the linker is calling the compiler, so it's just defined slightly differently. This gives you the amount of time internal things are happening within your code. For instance, total compilation time for this one source file. More importantly, the average time per function and which specific functions are taking all the time to compile. Here you can see our top 2 functions are pretty much 70 times more expensive than the other functions in the file. So you want to investigate those functions first. More likely, it's either force inline being used too much or heavy template usage, because, of course, templates also take more time to build. You will get mangled names out of there. There's a tool, UND name, command line tool, that'll unmangle them, so you get names like this. We talked about PCH files. There's this inline log flag, which will give you a full inline, all the functions are being inlined. Here's a simple function. It sets an atomic value to true. And you can see it's actually 7 levels deep within its inline functions. Even if an inline function is 0 lines of code, it'll still show up in this log, so you can go back and track it. We talked about the PCH files. There's this show includes. It'll give you the full include tree. So you can use this to try and figure out what you want to put in your PCH. You can kind of scrub it. So here it is for the frontier. You can scrub it across your entire library, count which file, the header usage for each of the headers, and from that decide what's going to go in your PCH, wherever that threshold is that works best for your title. Also, it's useful, this can show you if you have broken include orders on things, because you'll see the exact what the compiler is choosing to include at each level. So last call to action, yes, move to 2017, do it now as opposed to later. You're just increasing your software debt. It's definitely a more stable and scalable IDE. There's been a lot of work around basically those large monolithic solutions to be more stable. Of course, faster iteration on the compiler, your linker throughput, and
all about the C++ latest conformance. Yeah, absolutely.